Okay. So, can you guys see this empty white screen? Everybody?
Yes, sir.
Yes, sir.
Great. So, yesterday we saw the Hardy-Weinberg equilibrium, and as we pointed out that by itself that thing is not too interesting. Stuffs become interesting when we start looking at the deviation, and that studying those deviations is a full subject by itself. So what I'll do is I'll give you guys a quick glimpse of the kind of stuff that one can do in the context of one of the forces, namely selection. All right. And in the process of doing that, I will hopefully show you guys some things which make tremendous intuitive sense, but some other things which may not make that much of intuitive sense. Okay. So if you remember, we said that in according to the modern synthesis, evolutionary changes are supposed to happen when the gene frequencies change or the allele frequencies change. Now, like everything else in biology, there are counter examples everywhere, and I'm going to show you a counter example in which, in the absence of any of the four selection processes, gene frequencies will not change, but the observed genotype frequencies will change. And if you are observing the organism or the population from a distance, you will obviously assume that the organism is evolving. Okay, so this is just a simple counter example. So suppose you have a population in which there is some trait which is determined by a one locus two allele system, and the only change from the Hardy-Weinberg thing is that in this particular case, the population undergoes selfing. It doesn't undergo random mating. So suppose we have a population which is starting with all heterozygotes, and each generation this population is selfing. Okay, so when we start, p equal to 0.5, q equal to 0.5, and there is only one thing, capital S small a, and these guys, they keep on reproducing. So when they reproduce, what's going to happen? We are going to have capital A, capital A, capital A small a, and small a, right, in a ratio 1:2:1. Now when the next generation happens, these guys are going to produce capital A, capital A, these guys are going to produce small a, but these guys are going to produce 25% capital A, 25% small a, and 50% capital A small a, right? So you can see that as time progresses, this population is going to consist entirely of capital A and small a genotypes, which means phenotypically speaking, it has undergone what will look like divergent selection. However, there will be now two morphs which are completely different from the ancestral morph. However, if you look at the gene frequencies, the gene frequencies will still remain at 0.5, 0.5, and therefore, if you are simply tracking gene frequency, you will end up declaring that this population has not evolved at all. And note, when all this is happening, there is no selection happening, there is no mutation happening. All that is happening is that due to selfing, the and the underlying genetics of the trait, the trait distribution ends up changing. So this is an example wherein if you think about evolution in terms of gene frequency alone, you won't observe something, although something else is happening at the genotype level. Okay. So is this clear? Anybody has any queries on this? Because now I'll completely change tracks.
So here we are assuming that all reproduction occurs by selfing, right?
Yes.
But
Absolutely.
that's not feasible, no, because
Oh, no, no, no,
A
no.
and A small a can also reproduce,
No,
right?
no, no, no. See, there are lots and lots of organisms, for example, plants, etc., in which selfing is very common. Okay. So selfing is a well-known mode of reproduction. It's not a very uncommon thing at all.
But like, do the majority of organisms reproduce this way only?
More than 50%, probably not, but very large fraction, yes. In plants, yes. I don't know if
Okay.
animals we have hermaphrodites, but in those typically they don't self. Even if they have hermaphrodites, two of them will come together and they will end up, male to male, female to female. Sorry, male to female to male mating will happen. For example, in earthworms. But there are a significant number of plants which do this, mode of reproduction. Okay?
Okay.
So
Thank you.
it's not a hypothetical cooked up case. It's a very realistic. Okay. Okay. So let's get to studying the effect of selection, and we'll start with the very simple uh, one locus two allele case. So let's assume that we have allele A1 and another allele A2, and the frequency of allele A1 is P and the frequency of allele A2 is Q, where Q is equal to 1 minus P. Now let's assume that the kind of selection that we are going to study, remember I said that you can think of selection in two different ways. One, through differential number of babies being produced, and the other is through differential survivorship of the various genotypes. So the first one is called fertility selection, the second one is called viability selection. So what we are going to do over here is the simple viability selection model. Okay. So these are the gene frequencies or allele frequencies in the parents. So from this, we are going to go to the genotypic frequencies in the zygotes. So let's assume that till now everything is fine, which means that the genotypic frequencies will be in Hardy-Weinberg equilibrium, which means this is what is the stuff. So this is the genotypic frequency before selection. Okay. So this is still in Hardy-Weinberg. So now let's further assume that these guys don't have equal survivorship, which means that for each one of them we have a different value of survivorship. So let's assume that those values are called W11, W12 and W22. Okay. So you can see that when these things are not the same, then you have selection operating, and therefore you can think of these things also as genotypic fitness. Okay. So now once the survivorship step has happened, some of the these survivorship values have been realized, then post selection the frequencies of the various genotypes are going to be p square w11, 2pq w12 and q square w22, right? Now remember, p square plus 2pq plus q square, this stuff is going to sum to 1. But now when we have done this, these things will no longer necessarily sum to 1, right? So if we have to make them equivalent to this, that is, if we have to make them real frequencies, then we have to scale them. Now, what is the quantity with which we are going to scale them? The quantity with which we are going to scale them is going to be the sum of these three quantities, right? So what we are going to scale them with is p square w11 plus 2pq w12 plus q square w22, right? Now what exactly is this stuff: p square w11 plus 2pq w12 plus q square w22. This thing is the genotypic fitnesses scaled by the corresponding genotype frequencies, right? So in that sense, this thing is a weighted average. So it is the average fitness, right? Making sense?
Yeah.
Average
Yes,
fitness
sir.
scaled by the corresponding genotype frequencies. So this is what is denoted by W bar. Okay. So if this be the case, then W bar is equal to P square W11 plus 2PQ W12 plus Q square W2. So let's bring this thing over here. Then the frequencies after scaling and selection obviously is P square W11 by W bar 2PQ 2PQ W12 by W bar and Q square W22 by W bar. Correct? Now, just one. Huh. Now, what is going to be the frequency of A1 in next generation? Frequency of A1 in next gen. Okay, so this is typically denoted by P prime or P dash. So P dash is equal to, remember, P square plus PQ, right? Sorry, P plus Q by 2. So P is this, genotypic frequency is this. So this is going to be P square W11 by W bar plus, we'll take out the 2, PQ W12 by W bar equal to, I take the P by W bar outside, PW11 plus QW12. Okay. Now, what this is giving me is the frequency of the allele A1 after selection in the next generation, right? Now, we have a slight issue over here. The issue is that this thing is giving this stuff to me in terms of W11s and W12s, which are the genotypic fitnesses. Now, the reason we have to do this is because the fitness is only defined on the genotype. You cannot have a fitness which is defined directly or measurably on the allele, right? Therefore, in order to tackle that thing, we are going to do a quick, trick over here, a mathematical trick. And this trick, you might be familiar with it from the domain of economics, and that is figuring out the marginal allelic fitness. Now, what is the marginal allelic fitness? The marginal allelic fitness is essentially the average fitness of every single individual who has that particular allele in question. In this particular case, it will be A1. And this is going to be scaled by the corresponding frequency of those genotypes in the population. So I'll just show you what I mean over here. So let's assume that we are talking about the marginal fitness of allele A1. So this is denoted by W1 star. Okay. Now this particular allele A1, you are going to find it in two combinations. You are going to find it in a A1A1 combination, and you are going to find it in a A1A2 combination, right? In a one locus two allele system, that's all that it can do. So the genotypic fitness of A1A1 is W11. The genotypic fitness of A1A2 is W12. Correct? And now we have to scale this with the frequency of having this allele in the second position and having this allele in the second position. So if one allele is given as A1, what is the probability under the random mating and all other conditions of Hardy-Weinberg? What is the probability that this allele is going to be A1? See, think of the bean bags. Okay, we have picked out one allele, let's say from the male bag, and we know that it is A1. What is the probability of me pulling a A1 allele from the female bag?
P times W11. Oh, sorry,
It's just P. It's just P. No, it's not W1 star. Remember, fitness वगैरह जो है, all this viability selection etc. all this is going to happen later. Right
Okay.
now, just by itself, what is the probability of me pulling out an A1? That is simply P.
Yeah.
है ना? So that is what is going to scale this genotypic fitness. And similarly, what is the probability of me pulling out an A2? It's Q, right? So that is what is going to scale this genotypic fitness. So W1 star is equal to PW11 plus QW12, whereas W2 star, which is the marginal allelic fitness of the second allele A2, is QW11. Sorry, PW11 plus QW22. Yeah, sorry, extremely sorry, guys. I'm making a mess over here. So, W1 star is PW11 plus QW12. W2 star. So, in the context of W2, okay, W here this is going to become A1 A2 and A2 A2. So one allele is fixed, the A2 allele is fixed. Okay, so PW12 here and QW22 here. So this is going to be PW12 plus QW22. Making sense?
So shouldn't there be a half before the second term in the W1 star?
No. Why should there be a half?
Because you are taking the genotypic fitness of A1, right? So
Yes, I'm
in the in the A1 term, you will take the whole value, and from the A1 A2, you should take the half of the value, right?
no. Because all we are saying is that in the population, I have these two genotypes. That's all. Okay, this is independent of the genotypic frequency or anything. That half thing that you are talking about, that comes about in a specific situation where we are doing the Hardy-Weinberg under random mating, etc., etc. But this term that I am deriving, the marginal allelic fitness of allele A1, it is independent of what is the genotypic frequency, what law they are following, so on and so forth. All I am saying is that I have two genotypes in the population, A1A1 and A1A2. Then what is the sorry, I have three genotypes in the population, two alleles in the population. What is the marginal fitness of one allele and what is the marginal fitness of the other allele? That calculation is independent of the genotypic frequency.
Okay.
Bolo.
Sir, that female part getting A1, what is the probability? I didn't get that part.
मतलब I didn't get the question.
कुछ ना मतलब फीमेल एक होगा तो उसमें हम लोग को A1 मिलने का मतलब A1 मिलने का एलील मिलने का कितना प्रोबेबिलिटी है?
नहीं उस तरह से नहीं. देखो, so I have, suppose I am talking in terms of allele A1. Okay, so in terms of allele A1, I can only find allele A1 in genotype A1A1 and genotype A1A2. Correct? A2A2 में तो allele A1 मिलेगा नहीं. Right?
Yes,
now,
sir.
I have said that let's assume that one of the alleles is A1. So what is the probability that I am going to find A1 in the other A? What is the probability that, how do I put it? Okay, let me rephrase this whole thing. So the marginal allelic fitness is the average fitness over all individuals in which one of the alleles is A1. Okay, that's the definition. So if one of the alleles is A1, then that can happen in two ways, A1A1 and A1A2. Now, what is the probability of a A1A1 happening given that one allele is A1? That probability, it's a conditional probability, is P.
Okay, sir, got it.
Got it?
Yes, sir.
Similarly, what is the probability that the other allele is going to be A2? That allele is going to be, that probability is going to be Q. Okay, so that's how you get this P and this Q. All right.
Thank you, sir. Yes, sir.
So now, so W1 star is equal to PW11 plus QW12. Here, there is one more interesting thing to study. Look at this stuff. P squared W11 plus 2PQW12 plus Q squared W2. Okay. So I'll just write this again. Now what I'll do is I will simply take the Q term and I'll make it 1 minus P and I'll open the whole thing up. So P squared W11 plus 2P 1 minus P W12 plus 1 minus P whole square W22, which will be equal to P square W11 plus 2P W12 minus 2P square W12 plus W22 minus 2P W22 plus P square W22. Correct? This entire
Yes,
term.
sir. Yeah.
Okay. Do I need this? Actually, I need not have broken it down. मैं यहीं पे कर देता हूँ. Okay. So this particular thing, I can write this as P square W11 plus this 2PQW12. I'll write it as PQW12 plus PQW12 plus Q square W22. Okay. If I do that, here if I take the P as common, then I get PW11 plus QW12 plus I'll take Q as common over here. I get PW12 plus QW22, right? Now from these definitions over here, you can see that this stuff over here is actually W1 star, and this stuff over here inside is W2 star, right? Therefore, W bar is equal to PW1 star plus QW2 star. Can you see this relationship?
Yes, sir.
Okay. Now, if you think about this, what this is saying is that the average fitness, okay, which till now, remember, W bar has been defined in terms of genotypic fitness. The average genotypic fitness is essentially the scaled sum of the marginal allelic fitnesses. And scaled by what? Scaled by the corresponding allele frequency of A1 and allele frequency of A2. Okay. So in some sense, that should make some kind of intuitive sense. Okay. So now with these two things, we come back to this stuff. Okay. So we saw that P prime is equal to P by W bar PW11 plus QW12, which you should now realize is P by W bar into W1 star, right? Now, if we are trying to see by how much the allele frequency has changed over one generation, then what we do is delta P. And delta P is defined as P prime minus P. Okay. So, ouch. So, delta P equal to P prime minus P equal to P prime is what? P by W bar W1 star minus P equal to P by W bar, W1 star minus P W bar equal to P by W bar, W1 star minus W bar equal to, if you remember, we showed over here that W bar is equal to PW1 star plus QW2 star, right? Equal to P by W bar, W1 star minus PW1 star minus QW2 star, right? Equal to this thing over here. You can see that this is 1 minus PW1 star, right? So equal to P by W bar. Now 1 minus PW1 star is QW1 star equal to QW1 star minus QW2 star, which means equal to PQ by W bar, W1 star minus W2 star. Okay? Which again, just look at this equation over here. What is it telling me? It is telling me that the delta P, by how much the frequency is going to change, is essentially dependent on the product of the corresponding allele frequencies and the differences between their marginal allelic frequency. Okay. Now here you have to understand one thing. The W11s, W12s, W22s that we defined, those were genotypic properties. Okay. So until and unless the genotypic fitnesses are changing based on their numbers in the population, those things are going to remain constant. On the other hand, by its very definition, the marginal allelic fitness also has a component of the allele frequency built into it, which means the marginal allelic fitness is not a constant. As the population is changing, as the frequencies of the two alleles are changing, their corresponding marginal allelic fitnesses are also changing. Okay, this is a very important and interesting thing to note, which means as the population will keep on evolving, this product will also change and this difference will also keep on changing, simply because W1 star and W2 star themselves will be evolving. Okay. Now let us get to this point. Okay. So what we had done, we had taken the expression for W bar and we had simply opened it up to get this. Now if we want to look at the rate at which fitness is changing, dW bar dP with allele frequency, then dW by dP, differentiate the whole thing, is going to be 2pW11 plus 2W12 minus 4pW12, this term will go away, minus 2W22 plus 2pW22, right? Now in the process of making this differentiation, I have made an assumption. What is that assumption? What is that?
W's are constant.
Exactly. I have made the assumption that W11, W12 and W22s are constants. So that happens when the fitnesses are independent of the frequency. So this is why this stuff that I am going to do over here, this is frequency independent selection, or rather frequency independent genotypic fitness. Okay, genotypic fitness. That's what we are considering. Okay. So we will come back and we'll see what happens when we remove this constant. So I can take the 2 common outside. This becomes PW11 plus W12 minus, so I've taken 2 outside, so I have 2 PW12 over here. What I'll do is I'll make it minus PW12 minus PW12 minus W22 plus PW2, okay, equal to 2. So here you can see that this is W12 minus PW12. So this is 1 minus PW12, which is QW12. So this boils down to PW11 plus QW12. Is everybody clear how this is happening? I take the W12 common here, 1 minus P, multiply that with the W12. So Q into W12 minus, I take the minus outside. So I have PW12 over here plus W22 minus PW22. So again, I take 1 minus P common outside. So this becomes Q into W22, right? Which means equal to 2 into, this you can see is W1 star, 2 into W1 star minus, and this you can see is W2 star, right? So under the assumption of frequency independence of genotypic fitnesses, dW bar dP is 2 W1 star minus W2 star, which implies that W1 star minus W2 star is equal to half of dW bar dP. Correct? And now, if you are paying attention over here, if we come back to our expression for delta P, we can simply say delta P is equal to PQ by 2W bar. This is for that half dW bar dW bar dP, right? Which we can also write as delta P is equal to PQ by 2 D of ln W bar D. ठीक है?
Sir,
हाँ बोलो.
in reality, won't the W1 star and W2 star also be changing with the environment? With time, the environment will change, right? In any applied scenario.
Okay. See, W1 star depends on 2 quantities. Okay, by its very definition, if you look at how we are defining the W's over here, by its very definition, it depends on the genotypic fitnesses and it depends on the allele frequencies.
Right.
Correct? So W1 star and W2 star are anyway constantly changing, even if your W11 and W12 are constant.
Right.
So even if the genotypic frequencies by themselves are not changing, marginal allelic fitnesses are always changing.
Okay.
If the genotypic frequencies are also changing on top of P and Q, then of course it will be changing even more.
Okay.
Okay. But I mean, you don't even need to, invoke the environment or selection or anything to know that the marginal allelic fitness is a constantly changing thing.
Okay.
Okay. So these two equations are known in the evolutionary biology literature as Wright's equation for fitness landscape. Okay, you guys might have heard of adaptive landscape or fitness landscape, these kind of terms, and you guys might have heard about, seen those, nice hills and valleys and all that. Has anyone seen those kind of diagrams?
Yes, sir.
So the person who first gave that was this man called Sewell Wright, and he is supposed to be one of the 3 or 4 core members whose work in population genetics put the field on a very firm footing. He was the guy who talked a lot about genetic drift, which again we are going to hopefully study at some point. Basically, this is one of the major conceptual giants in the field of evolutionary biology. Okay. Now, if you look at this thing, simply look at it, then let's look at this equation. I personally find this to be always much simpler to predict, much simpler to understand. So if you look at this, then you see that by definition P is going to be between 0 and 1 and Q is also going to be between 0 and 1. So these two things are always going to be positive, okay, which means that this stuff over here, the delta P, the sign of delta P is always going to be determined by the sign of dw bar dp. So which way P is changing, plus or minus, the sign of that is simply a function of dw bar dp. So if that be the case, let us look at dw bar dp in a slight greater amount of detail. So this is the expression for dw bar dp. So let's do the double differentiation. Okay. So the 2 is already outside. So what we are getting is W11. Okay, let's do it over here. W12 terms goes 11 minus W12. Actually, it will be minus 2W12 because there are two of those. Minus 2W12. This term goes plus W22. Right? Now, which means this is equal to 2 W11 plus W22 minus W12 minus 2W1. Okay. Now you know that whether there is going to be a maxima or a minima in the W bar against P graph depends on the sign of this, right? So from this you can see that if W11, W22 are greater than W12, then the sign of this is going to be positive, which means we are going to get a minima. And if W11 and W22, both of them are less than W12, then the sign of this is going to be negative, and that means we are going to get a maximum. Okay, makes sense? So if we plot these three cases, okay, when I've talked about only two, but there will be three cases. So we have W bar on the y-axis in all the cases, and we have P on x-axis in all the cases. Then if we have this scenario, then we are going to get a graph which will look like this, and we know this is going to look like this because this is a quadratic in P. If we so this is the scenario where W11, W22 is greater than W1. This is the case where we are going to have the reverse. So this is the case where W11, W22 is less than W1. Okay. And there is a third case in which you won't have some kind of an internal maxima or a minima. You will get some other thing which will go like this. Okay. Now, in this particular case, we have a scenario where both homozygotes have greater fitness than the heterozygote. This is what is known as underdominance. And here we have a scenario where both homozygotes are less fit than the heterozygote. So this is what is known as overdominance. Okay. This is what is known as overdominance. Now, what's going to happen? I mean, this obviously is a stable point. What is going to happen if the system is, let's say, here? Okay, what is going to happen?
P will increase.
Remember, delta P sign depends on dW bar dP, right? That's what I showed you guys over here. That's what I showed you guys over here. That's what I showed you guys over here, correct? Now, over here, what is the slope of dW bar dP over here? It's negative, correct?
Yes, sir.
So P is going to decrease over here. So if P decreases over here, what will happen? W bar will increase, correct? Similarly, in this zone, if P increases, then the slope is positive. Then, so basically, the population is going to go like this. This is the behavior of the W bar, correct? Similarly, in this particular case, here the slope is positive, so it will go like this. Here the slope is negative, so P will move like this, but the fitness will go like this. So this is a stable equilibrium point, whereas this one is a unstable equilibrium point, right? And in these cases, it's very easy. Whenever P increases, it's always going to go up. There is no other thing that it can do. So the fitness will go, the average fitness will go like this. So what we are seeing from this is that irrespective of the scenario, whether whatever is the relationship between the three fitnesses, the three genotypic fitnesses, the W bar is always going to increase in the population. There is nothing else that it can do. Okay. Now, this kind of analysis is what leads to the intuitive understanding that selection always increases fitness. Okay, at the population level, obviously, selection always increases population fitness, and that you can see is very easily and very nicely borne out from this, right? Okay, we have come to the end of the class, 45 minutes. So we'll stop here. In the next class, we are going to go one step further and we'll ask the question that what happens if we end up removing this condition? What happens if the frequency or if the genotypic frequencies are, genotypic fitnesses are frequency dependent? How does that change this simplistic picture? Okay. So yeah, I will stop the recording now. Oh, and it goes to Raghunandan DR's Google Drive. Why does it always go to Raghunandan's Google Drive?